Hello, I am Channa Bankapur. I'm going to discuss my solution to the lead code problem bag of tokens. It's today's problem in the October lead coding challenge. The problem definition is as follows. We have a bag of tokens. That means an array of tokens with some non-negative integers. And we have some initial power p that is also non-negative and an initial score 0. The objective of this problem is to maximize the score. That means we want to score as much as possible, and the way of scoring is if the current power is at least as much as one of the tokens, we are going to use it on this token to get one score, and the power is going to be reduced by the value of the token, right? So that's how we are going to use the power to score one. And if there is not enough power to even use on any of the tokens, then we are going to spend one score. That means we lose one score to increase and increase the power by whatever the token value by spending one score, right? So obviously in this case we need to have at least one score to even do this operation. All right, so that's the idea here. Let's go with a couple of examples to understand it better, and then find a method to solve. So the first problem, we have only one token and power 50. We cannot buy this, or we cannot actually use this on use the power on the token to get a score. And yeah, so obviously you cannot even increase the power also because the score is 0 to start with. So that's what the answer is. And for the second example, we have a power of 150 to start with, so we can use it on one of the tokens and get one score. But after that, there is only one token left out, and so if you want to increase the power, there is no point in doing that. But because you're going to spend on the spend the only one score you have on the token, and you don't have a way of gaining that another score, right? Because both tokens are already used up. So that's why the answer is only one. The third example is little more elaborate. So we have an initial power of 200. So we can actually use on any one of these to start with. But as in, because there is no clear difference between any one of them, it doesn't matter where they are. So I'm going to just use it on the smaller one because at least I'll be left with more power, right? And because I'm going to gain only one score, right? No matter which token it is. So I'm going to use it on the smaller token and gain one score. So right now my power is reduced, say from 200 to 100, and also I have a score of one. So now I cannot use it on the second token. So this is the time I should increase my power by spending a token. So I'm going to spend this token, whatever I'm going to spend this score, whatever the score I have, on one of the tokens. So which token I want to use it on? I want to increase the power, right? Anyway, all the tokens are going to cost me one score. So I'm just going to use it for on the maximum valued token, so that I'm going to increase power as much as possible by using one score, right? My score is reduced to 0. So this was already used up earlier, and now this is used up. So now I have 500 score. I'm going to go with again 200 because it is smaller. So my power is reduced to 300 with a score of 1. And I have one more token which is of 300 value. So power is going to reduce to 0 with a score of 2. And all the tokens are used up, and yeah, we don't have any way to go. So that's why my answer is 2 in this case, right? So at least for now, I'm already getting a greedy method here. Even though it's an optimization problem, I should be using some exhaustive method. While choosing, I should try out all possibilities and see which is going to be optimal. But instead of that, what I'm going to do is see, I have some power. I want to increase the score, right? Increasing the score is the objective. All right, so I'll try to use it on tokens, and when I'm using on a token, instead of when I have multiple options like this, I'm going to use it on the one which has the lowest value, because that is going to increase, that's going to leave more power with me, right? More power is better because I can buy more tokens, or I can score more by using on tokens. All right, and also that's how I'm gonna start with the lowest valued token for using power to gain score. But when I don't have enough power, I need to use on a token to gain the power, right? I need to lose a score on a token to gain the power. In that case, because more power means I can buy more, I can use on more tokens and then get more score. I'll try to use the maximum value token on this, and that's how I get more power, because all of them cost me one score, right? So that's why the problem is kind of simple to me. I'm going to sort all the tokens in ascending order, right? So the smallest value to highest value. So as in this problem, it is already sorted. If it is not sorted, I'm going to sort it anyway. So, and I'll start from here for, gaining the score by using power. And whenever I don't have enough power, I'm going to start from here on the reverse, on the reverse direction, to use the score to gain the power, right, on a token. All right. But yeah, my approach is I'm going to start with, trying to use the power as much as possible. So that's why, as long as we have enough power, I'm going to keep buying, keep using on the tokens to get the score. All right. So here, okay, in this case, it's very clear. I'm going to buy, I'm going to use on this one, and then I increases to this point, and score is 1. Now I cannot, power is reduced to 100, so I cannot use it on this one. So that I'm going to increase the power by actually spending on this token, or actually spending the score on this token. So score is going to go up to 500. Sorry, the power is going to go up to 500, and J is going to come down here, right? So now we need to figure out when to stop it. When I is equal to j, that means there is only one token left out. And when there is only one token left out, even if I don't have enough power, I don't want to spend on that token to increase the power, because that is going to be spending the score, and will not get a chance to again, increase the score anymore, right? So that's why, if I is less than or equal to j, sure, I want to still see whether I can increase the score, because there is still that token left out. But if I is equal to j, then only I want to increase the power. So this is the idea I'm trying to use. Let me show you the code, which is going to be more clearer. All the points are kind of covered here. See here, I have sorted the tokens already, and then so I is pointing to 0 and j is pointing to n minus 1. That's the last one. So score is 0 to start with. So as long as I is less than or equal to j, that means as long as there is at least one token left out, I'm gonna, if power is as much as that the current token, which is the smallest token available, I'm gonna use it on that token, right? So that the power is reduced by that and score is increased by 1, right? And I obviously moves because that token is used up. If I don't have enough power, so if I have enough power to even buy the next token, what I'm going to do is I will, just go in the while loop and then keep doing this one, right? So that's why this if condition is good enough. If I don't have enough power, I need to increase the power, right? So, but I don't want to increase the power if that is the last token left out. That's why if I is less than j, then only I try, because I is less than j indicates there are at least two tokens. So if I spend on the more value token, I can gain at least one score by spending on a lesser value token. So that's why if I is less than j, and obviously by the problem definition says if score is at least 1, then only we can do this operation. So if score is greater than 0, then I'm going to gain that power, and by spending the score, and obviously j decreases because we are going in the reverse direction. If neither of these two happens, that means we are stuck, right? That means we cannot do anything, and in that case I'm going to break out, right? So this is that one case we you may want to think of. And in so this case is needed, because when I is equal to j and we don't have enough power, we go to this method, and this is also going to be failed. So that is the only case actually I need break for, right? So, and that's how I come out of this one, and then finally score is the answer I have. So let's see whether it works. The sample test case is too trivial. It works, but let's submit and see whether it works for all. It worked for all. All right. And if you see the time complexity, or actually how fast it runs, 84-85 percentile is actually pretty good. That means our solution is at least optimal. Um, So what is the time complexity of this? If you see, we sorted them initially. So if there are n tokens, we took like, big of n log n time to sort it, right? And then after that, it is linear time, method, because we start with I is equal to 0 and j is equal to n minus 1. And in every loop, if we are not breaking out of the loop, we are either incrementing I or decrementing j. That means the range of I comma j is always reducing by 1. So that, and all these operations are linear time operations. That's why it takes linear time afterwards. So sorting is the significant operation in terms of time complexity. So the overall time complexity is big O of n log n. All right. So if there is any other method, you can without actually sorting it, because sorting is going to cost you big O of n log n. Then let me know in the comments. Otherwise, please subscribe to the channel and like the video, and keep coding every day. Thanks for watching.